I'm Cherie Day, a final year PhD student at Swinburne and CSIRO, and I work with the Craft and Utmost 2D collaborations. Welcome to what has a 1 in 3 chance of being your first primer of FRB 2021. So I invite you to pull up a chair, get comfortable, and let's chat FRBs, specifically finding and localizing them. All right, so there are a few primers on the conference website this year, which is fantastic. And they're focusing on some of the major topics you'll run into over the course of this week and next week. So do check those out as well if you haven't yet. But for now, the general goals of this primer are: 1, how do we find or detect FRBs? There are some specific FRB properties to keep in mind here, so we'll start off with those, and then we'll move into some search techniques and how we actually go about observing FRBs, and then we'll talk about some of the trade-offs when it comes to experiment designs. Then we'll go through some of the basics of localization, the options we have, and then some things to watch out for, and the experiments currently in the localization game. Now, clearly, I can't go into too much detail in a relatively short talk, but my main goal here is to give you more of a broad overview and a good starting point. So let's dive right in. As the name suggests, FRBs are short duration of order micro to milliseconds. They're bursty and they emit in the radio. So they're impulsive and have variable widths, but they're also dispersed. We can see that in the plot here, where we have a dynamic spectrum in the lower panel. So that's frequency versus time versus intensity in color. And then we have the pulse profile in the top panel. So dispersion occurs when the pulse propagates through ionized material and interacts with all the electrons it encounters along the line of sight. And that causes the lower energy waves, or lower frequencies, to be delayed relative to the higher ones. So we get this nice quadratic sweep in the frequency arrival times. We quantify this dispersion using the dispersion measure, or DM, which is the integrated electron column density along the line of sight. So when we observe an FRB, this is how the pulse arrives at our telescopes, one frequency chunk at a time. So once we've captured the burst and we have its DM, we can de-disperse it, or effectively shift all those frequency chunks over so that they line up nicely. Then we can average over frequency to get the pulse profile in the top panel. Now, resolution matters here in 2 ways. For temporal resolution, the higher it is, the better we can line up those channels, or equivalently, the more accurately we can estimate the DM, as we can see in the right set of plots, which are at higher time resolution, which also brings out that scattering tail of the burst and allows us to better determine its width. But to hear more about measuring the properties of FRBs, be sure to check out Cherie's primer. We also have to remember that our bandwidth is finite, so we're splitting it up into a finite number of channels, and since the pulse will be dispersed across each channel, there will always be some residual dispersion we can't correct. And that results in what's called dispersion smearing. So the higher the resolution, the better our DM estimate is, and the more fully we can correct for the total dispersion. So at this point, you might be very rightly thinking that this all sounds a bit tricky. I mean, first of all, we need a system that can capture data fast enough to even be able to see these FRBs, and that can get computationally expensive fast. And then they can show up anywhere in the sky and at any time. So unlike persistent or continuum radio emission, we're effectively searching blind. We also don't know exactly what the observed properties will be in advance, like the pulse width or the DM. So when we're searching, we have to form what we call beams, which I'll get back to, pointing in a given direction, and then do a mountain of searches over trial DM and width combinations until we finally get a candidate. Now, a partial exception to our not knowing anything in advance is when we're following up repeaters. In those cases, the TM is fairly well constrained, and depending on the precision of any localization, the location might be well known enough for a given instrument to effectively point right at it. Okay, so you've got yourself a candidate now, yes, but it turns out to be radio frequency interference, or RFI, which is the bane of all radio astronomy. So these are man-made transmissions, not astrophysical, and definitely not that FRB you were hoping would break the mold and solve the mystery that is FRBs. Sigh. But unfortunately for us, RFI can be dispersed and can look enough like an FRB, to a computer at least, to make it through as a candidate. And since RFI events can happen thousands of times a day potentially, rather than trying to visually inspect all of those candidates, we need some kind of automated classification system. So we use machine learning algorithms to accomplish this and thereby reduce the false positive rates. This is especially important when an experiment wants to automatically trigger follow-up observations. No one wants to accidentally trigger a follow-up of a phone call. Anyway, once you've got that classification algorithm running like a well-oiled machine, when you get that notification that you've found an FRB, it's far more likely that you have indeed found one, and when you have, then you can really start to have some fun. All right, so we have an idea of some of the technical aspects of detecting an FRB, but how do we actually observe them in the first place? And what were those beams I mentioned earlier? Well, we do at least our initial observations with radio telescopes. The exact specifications can vary, but fundamentally, each telescope senses or measures the incoming electric field. Essentially, it converts the electromagnetic wave into an electrical signal and encodes the received information in the voltages of that signal. Hence, we call them voltages. And they can carry both the magnitude and phase information of the waves. Now, every telescope has a beam pattern. This is the gain or sensitivity or response of the telescope to that electric field as a function of frequency and angle. So I'm showing one example here from Krauss's Radio Astronomy, which is a classic. Highly recommend if you can get a hold of a copy. But beams can have all different shapes and sizes, even for the same telescope, depending on the frequency. Now, the sensitivity peaks at the center and drops off as you move away until you get to the first null, at which you have no response. But beware, beams can also have minor lobes, often called side lobes, and these can have non-negligible responses. So when you hear people talking about an FRB detection potentially being a side lobe detection, that's what they're referring to. Finally, beams can be either physically or electronically pointed at a set of coordinates. In the first case, we're physically aiming the telescope at a given sky location. And in the second case, we can effectively point the telescope by introducing signal delays or phases that approximate delays for narrowband instruments. So whether this is a primary beam, your basic beam unit, if you will, or a synthesized beam where you've combined multiple beams, the end beam product can be described in this basic way. So with that beam description in our minds, we can take a look at what different FRB detecting experiments can use. We have single beam instruments like Arecibo, which is sadly no longer with us, the Green Bank telescope, or the ultra wideband receiver on the Parkes 64 meter. Then we have a couple flavors of multi-beam instruments. We have the physical variety, for instance, the multi-beam receiver on Parkes that used to be on Parkes, and I'm showing the footprint of that in this top image here. So with this, each beam samples a different region of the dish's focal plane, effectively behaving like 3 single beams. And this results in each seeing a different patch of sky. Then we have the electronic or phased array feed variety. And here each feed samples part of the focal plane, and the path beams, or electronic primary beams, are formed by weighting and summing the feed voltages. So this is replacing what happens optically in the physical multi-beam system with electronic combination. And that gives us a lot more freedom. For instance, the patches of sky seen by each beam can be made to overlap, as we can see in the bottom image of the ASCAP path footprint. Now, this allows for greater accuracy in determining the position of a source within the beam, and thus its localization region. But I'll come back to that in a little while. We can also combine multiple telescopes, and again, we've got a few options. We can form incoherent beams where we sum the voltages squared, or equivalently the electric field powers or intensities. So here we're discarding the phase information. We can coherently add the voltages one beam at a time, and that preserves the phase information. Or we can image. Now, this is the same as what a normal radio interferometer does, measuring coherence between pairs and doing a bit of signal processing magic to get lots of pixels simultaneously. Only in our case, we need to make a lot more of them on short timescales. So regular magic, but done really fast. It's worth noting here that typically FRB searches are run on the total intensity data, so throwing away the polarization information, since this helps to reduce the data volume in general. So as the title of this slide suggests, there are some trade-offs when choosing your beamforming method or setting up the experiment in general. Incoherent beamforming preserves the full field of view at the cost of sensitivity, although it's still more sensitive than a single beam by a factor of the square root of the number of antennas. So that's good. Tide array beamforming, on the other hand, gets you full sensitivity at the cost of field of view. These are important trade-offs to keep in mind when designing FRB surveys. Experiments like CHIME or ASCAP are capable of catching lots of FRBs because they have large fields of view. Any given FRB is just more likely to be within your field of view if it covers more of the sky. But the more sensitive the telescope is, the better able it is to detect the weaker or more distant FRBs. So at the end of the day, it all depends on what your goals are. All right, so now we know there are different kinds of beams and ways of beamforming and some trade-offs. So what do these give us in terms of localization? Well, if it's a single beam, nothing really. There's no real way to tell exactly where the FRB is within the beam, so not really helpful. If we have multiple beams, however, either on one telescope or multiple telescopes, then we've got some options. And these boil down to two categories depending on whether or not you have voltages. Again, voltages are just the representation of the electric field with both phase and magnitude information. You'll also hear them referred to as baseband or raw data. So if we have voltages, fantastic, but if voltages aren't saved, then we're dealing with the power or intensity data. All right, starting with the case of having only the intensity data, say we have an FRB that's detected in multiple beams. In the figure here, we have detections in several ASCAP path beams with signal-to-noise ratios given in color. Now, the precision of the FRB position can be improved by combining both the detection signal-to-noise in each beam with beam models, essentially using this combined information to get a probability of where the FRB is in each detection beam and therefore where it is on the sky. CHIME and ASCAP in its incoherent submode both do this, for example. And I'll just note as well that the figure here does show an extreme case of a super bright burst from a repeater detection with ASCAP, so normally you wouldn't see it in so many beams. If we do have the voltages rather than just intensity data though, then we can go the interferometry route and make radio images. Again, this is similar to regular radio imaging, but using a matched filter of sorts in frequency and time. Essentially, we want to only get the part of the frequency band in which the FRB emits and the chunk of time within the full data stream in which the FRB is on. Anything else just adds noise, decreasing the signal to noise, which we don't want. So once we've made the image, something like the one on the left here, we can fit a centroid to the source, read off the position, and then we just add it over an optical image like the one on the right? Well, not quite. The precision to which we can read off that position depends on the signal to noise. And the accuracy of that position also depends on how good our calibration solutions are. If we haven't calibrated well, then the image can appear in the wrong part of the sky. To illustrate what I mean here, let's take a look at a simple example of a two-element interferometer. We have a source emitting a radiation that arrives at our telescope as a plane wave. And fundamentally, we're measuring the relative delays in the signal between the two antennas. Tell you what, let's get crazy. Let's add in some atmosphere and some ionosphere just to make this a bit more realistic, right? Yeah, okay, that's a lot better. So a pair of antennas will measure an arrival time delay that depends on where the source is. And we can make and apply a model that has a nominal source location. And if that's correct and everything else is perfectly modeled, then there will be no relative delay. Cool. And in this example, we've done it all correctly. And so the signal is arriving at both antennas at the same time. Another important quantity I'll just mention here is the baseline, or the separation between the antennas, as seen by the source. The longer the baseline is, the higher your angular resolution, and in turn, the final positional precision. But what if there's a bit of a delay between the signal arriving at one antenna relative to the other, right? In other words, it doesn't arrive at the same time or at the same time at both antennas after we've made our best model. Well, then the source will appear to be in a different position. You can think of it like this. That extra delay changes the apparent angle of the plane wave in this 1D example, and that changes where the source appears to be. So long story short, the quality of our calibration solutions dictates the amount of degradation of the astrometric accuracy of our positions relative to the native instrumental resolution. The best you can do is the beam size divided by the signal to noise. You can only do worse from there if your models aren't quite right. In other words, if you start with higher angular resolution, then the same quality of calibration as a lower resolution instrument will still give you a higher level of accuracy in the position because you've started off with higher accuracy. Now, typically we can get to somewhere between a 10th and 100th of the beam size, depending on the signal to noise, and that in turn depends on how good your calibration is. So if you're using, for instance, very long baseline interferometry, or VLBI, which has beams of order 5 milliarcseconds or so, then even with a less than perfect calibration, you're still localizing at milliarcsecond levels. Different telescopes have different methods of calibrating and quantifying the extent of any systematic astrometric shifts, but bottom line, the amount your positional accuracy degrades depends on how good your calibration solutions are. And both the precision and the accuracy of FRB positions have very practical consequences. For instance, they can make or break your ability to associate an FRB with a host at all. Or your localization region might cover a whole galaxy, so the best you can do is differentiate between hosts, like the case of this bottom one here, where the precision's only a few arcseconds, or about a 10th of the ASCAP beam. But as your precision gets higher, you can start to pinpoint more exactly where the FRB originated from within the galaxy, like 18024 in the top right figure here, where we know it's coming from the outskirts. Now, this position has a sub-arcsecond precision, or about 100th of the ASCAP beam, And that's why we can know that. So, and just to note that these two precisions cover the range that we normally see with ASCAP. All right, so then we get into VLBI territory with milli-arcsecond precision, and you can really start to home in on the local environments of FRBs, which is super exciting. And we can see that in this bottom figure here, where the European VLBI network was used to localize FRB 180916 to this star-forming clump in its host spiral arm. And just to note, at a resolution of a little more than a few milliarcseconds and an accuracy of about a few milliarcseconds, you don't have to get a very small fraction of the beam size before you get a ridiculously good precision when using VLBI. And as the examples here show, the name of the game is definitely sub-arcsecond precision when it comes to characterizing local environments. But it's also worth emphasizing that it's not just about precision. We also need to know how reliable, how accurate these positions are in order to confidently interpret what we're seeing. On the one hand, underestimating our uncertainties can lead to erroneous conclusions, but on the other hand, overestimation results in losing the ability to infer any local characteristics from the position. So, in our quest to determine the origins of FRBs, we really need both high precision and high accuracy positions. So I've shown you some ASCAP and some EVN results, but the list of current players in the localization game is growing. We've got the of order 1 to tens of kilometer baseline experiments, VLBI. There's a bit of a gap in between. Then there are the wide field instruments like CHIME and ASCAP. And while at the moment, CHIME has only localized a small number of FRBs, partly because its baselines are so short, once they get their outriggers up and running and Chord comes online, that'll shift them over into the VLBI territory. There are ones that use the tight array beamforming we talked about, like Utmost and Meerkat. And Utmost 2D, once that's fully operational, it will be able to associate most of its detected FRBs with host galaxies, which is very exciting. So for some very exciting updates on that, make sure to check out Adam Deller's talk in plenary session 8. And then there's RealFast as well on the VLA, and that forms images at high time resolution and searches for FRBs in the image plane. Now, each experiment has its strengths and weaknesses when it comes to finding and localizing lots of FRBs, but happily, they do tend to complement each other quite well in terms of the observational phase space they occupy. With room for improvement, of course, as with all things in radio astronomy, or astronomy in general. All right, well, that's about it from me, but I do want to leave you with a few extra resources that you might find useful. These are more general and less FRB specific, but they are fantastic resources that every radio astronomer should have at their fingertips. I've included the links to those that are available digitally for free, which is most of them. Otherwise, they should be available at any university library. And if you're looking for a more of a deep dive into the world of characterizing astrometric accuracy, specifically for FRBs localized with ASCAP, then in fact, also how you too might be able to go about doing similar work for your instrument, then definitely check out my recent paper on the archive. And since this is on YouTube, then all these links should be in the description box below. And if you have any follow-up questions, feel free to message me on the conference Slack using @Cherie. All right, well, thanks for listening and have a fantastic FRB 2021.